All right, so this talk is MPLS for Dummies. If you're looking for MPLS for brain aneurysms, it's down the hall and up the stairs. This is the non-insane one. The purpose of this tutorial, there's a lot of people out there, classic IP people, who still don't like MPLS. There's a lot of concepts about MPLS that are really pretty foreign to classic IP networks. And there's lots of parts of it that kind of smell like ATM, which was a technology that really didn't get well deployed in the IP world. And there's a lot of aspects of MPLS that you could call overly complicated. And there's a lot of aspects of it that you could say may not have been presented well for pure IP networks. And honestly, there's a lot of networks out there. There's a lot of networks who claim to run MPLS networks, who put it on their slicks, but they're not actually using it to their full potential. They may have it enabled and they may do a little bit of transport over it, but they aren't using it for traffic engineering, or they aren't using it fully. So the purpose of this presentation is to talk about how MPLS can benefit you. So with any luck, we're going to talk about basic concepts for people who haven't done MPLS before and show you how you can make your network better with it. So here's the target audience. This is Dave Bannister's car. And I promise it's not ATM 2.0. Even though I like those plates. So, the basics of MPLS. MPLS stands for multi-protocol label switching. And if you had to describe it in 4 words, you call it layer 2.5 networking protocol. In a traditional OSI model, you have your layer 2 that covers your technologies like Ethernet, SONET, that covers things that transport a packet, a frame, from point A to point B. And then you have layer 3, which covers global routing across the internet. MPLS basically is a new layer that sits in between these 2 existing layers that lets you carry packets across a WAN in a special way that's not IP. So it lets you add features to your IP services, and it lets you add transport features that you otherwise couldn't get with IP. So in a traditional IP network, what happens is each router performs an IP lookup. It's called routing. You find the next hop. You look at your routing table, you find the next hop, and you forward the packet to that next hop. And you do that independently each and every time for each and every router until the destination's reached. So it's kind of like if you were handing off a package to UPS, and they looked up the destination and they figured out how to get it to, across the world where you're trying to send it, and then handed it to the person next to them, and then that person did the exact same thing over again. You're repeating the same process over and over and over again. You're doing a full routing lookup. What MPLS does is called label switching. So what happens is the first device does a routing lookup, just like before, but instead of finding the next hop and forwarding it off, you have the final destination router, which everyone knows from looking at the routing table, and this time you slap a tag on the packet, and the tag adds some information. It predefines a path that you're going to use to forward this packet through the network, all the way from here to the final router. The tag is called a label, or called a shim. The shim is basically just the MPLS header that gets slapped on the packet. And future routers, when they see this tag, they look at that instead of having to do an IP routing lookup. And then when you get to the final destination, the label gets removed and the packet gets handed off like normal. So if you look at historically at what MPLS came from, originally it was intended to reduce routing lookups. So when CIDR was introduced, before CIDR, there was no such concept as longlist prefix matching. And with CIDR, you would get this. So now you have to kind of look at a tree to do a routing lookup. You might have a /24 that's a member of a /19, that's a member of a /17, that's a member of a /16, and you've got to find what's the most specific prefix in your routing table. So to do this, it's actually historically been pretty difficult. What was done historically in software was a routing table with a lookup called a Patricia tree, which is just a bit tree where depending on how many more specific prefixes there are, the tree can be pretty deep. And so you have this indeterminate lookup. You're not sure when you start this thing how long this lookup's going to take, how many memory accesses it's going to be, and it can be a lot. And it turned out that was actually pretty difficult to implement in hardware. Comparatively, exact matches are much easier to implement in hardware. And if you look historically at how the first hardware routers were created, really what they did was they cheated. They had the first packet of the flow looked up in software, and then they programmed those results into hardware, and then they did an exact match based on that. So you kind of end run the whole problem of having to do this lookup. The problem there is you don't get consistent performance. You might get millions of packets per second from a pre-programmed route, but you might get a couple of hundred packets per second if you actually have to punt it to software. So label switching was originally intended to help work around this. So the idea was you would distribute the load. You would only have to have your first edge router do the lookup, apply the label, and then all future routers would just be able to look at the label and do an exact match. And this would reduce the load on the core routers, which was where the work was the hardest for things to get done. That's where people were having the most problem making a box that could actually keep up. So modern ASICs have mostly eliminated this issue, but I'll say mostly, because while, yes, you can purchase a commodity ASIC that does tens or hundreds of millions of lookups per second for a few $100s, they actually still make up a significant portion of the cost of the box. And if you look at some of the hardware that's out there, you can actually, even today, get double the performance or 4 times the performance at a quarter of the cost for a layer 2 only box. And the difference here is purely exact match versus having to do a longest prefix match lookup. So it's still, even though it's been solved, it still adds a lot to the cost. So why do people care about MPLS today? There's 3 reasons at this point. Number 1 is to implement traffic engineering, which just means controlling how the traffic goes around your network to manage capacity, prevent congestion, prioritize things however you want. Number 2 is to implement multi-service networks, which means not just IP. You can also carry data. You could replace historic frame relay, ATM, et cetera, et cetera. And number 3 is to improve network resiliency with MPLS Fast Reroute. So, how MPLS works. The most important concept of using MPLS is called an LSP. It's the label switched path. So what this is a unidirectional tunnel from one router to another router across your MPLS network. Basically, you need an LSP to do anything with MPLS. That's the most fundamental unit of actually doing something. So within your MPLS network, there's a couple of roles that the devices play. One's the label edge router, also called the ingress node, and that's the router that first encapsulates the packet. That's called pushing the packet onto the stack, or ingress basically. That's the router that does the first routing lookup and applies the label. There's the label switching router, which is a transit node. Basically, it's somewhere in the middle. It's a router that just looks at the MPLS label, may swap the label, but it's just passing it through purely as MPLS. It's not doing any deeper layer. And then there's the egress node, which is the final router of the LSP, which removes the label, or we'll get into that in more detail in a bit. Some MPLS roles are also expressed as P or PE. Basically, these terms come from the VPN services. So the 2 roles that you'll see in a provider network are the P router, which just stands for a provider router. It's the core router in the middle that's just doing label switching. And a pure P router can actually operate without any customer or internet routes at all. It can just purely switch on MPLS. And there's actually a lot of large service providers out there that implement it that way. The PE router is the provider edge router. This is the router that does the encapsulation or the popping or the imposition. So it's at both ends of the LSP. And basically this type of router does your services. It does your internet, it does your L2 VPNs, your L3 VPNs, your pseudowires, your VPLS. And then the other role, you'll see a CE and a C, which is just the customer side of this. So the CE touches the PE. The PE is your router. The CE is your customer router. You'll see this in diagrams for describing VPN services. So there's MPLS signaling protocols. So in order to actually use an LSP, you have to signal it across your routers. So an LSP is a network-wide concept. technically it's only expressed across the routers where it needs to travel, but basically it's a network-wide concept. It goes from one end to the other, and every router that needs to know about it knows about it. A label is actually a link local value, so it has no meaning other than to the two routers that are talking immediately next to each other. And you have a signaling protocol that takes these LSPs and translates them into labels and pushes them out to the routers that they need to go to. So the two main types of MPLS signaling protocols are LDP and RSVP. Technically it's RSVP-TE because RSVP was originally a specification for just generic reservation. It had nothing to do with MPLS. And then they took that and they extended it to be specific to MPLS, and that's called RSVP-TE. Most people just call it RSVP for short. So the difference is LDP, Label Distribution Protocol, is a relatively simple, relatively lightweight, non-constrained, which means it doesn't support any kind of traffic engineering. It's a very simple protocol for exchanging labels. RSVP is a much more complex protocol, has more overhead, but it supports traffic engineering. Basically, you're out making network reservations. You're saying, I'm taking this much capacity, don't let anyone else use it. And what you'll actually see in practice is most networks will end up using both because LDP is typically used for your MPLS VPN services, and then what will happen is you'll tunnel the LDP inside an RSVP tunnel, and that will do the traffic engineering across your network. MPLS labels can be stacked multiple times. So the top label is what's actually steering the packet at any given moment. And you can add new labels on top of that. You can take an existing MPLS packet and you can stick it inside another MPLS header. The top label is controlling whatever's going on. When you get to the destination that you're trying to reach, that label gets popped. And then if there's another label under that, you can continue forwarding the packet via whatever you're trying to accomplish. Some common applications for this are VPN or transport services. And what you're doing there is you're using the inner label to map a specific transport instance. So it's going to map all the way out to a specific customer transport instance out to an interface. And the outer label is going to be responsible for routing through your network. You'll also see this in bypass LSPs, which we talk more about later. And that's used to protect a bundle of other LSPs without having to resignal them. So there's a little diagram that's showing you can take an LSP and stick it inside another LSP. There's a concept called Penultimate Hop Popping, which is basically just a really tongue-twisted way of saying having the router before the next to the last router do it instead of the last router. So there's two ways to terminate an LSP. One is called implicit null, which is penultimate hop popping. And basically what's happening is you're popping the label before the final router, so when the packet actually gets to the final router doesn't have to do two steps. You can configure explicit null, and basically when you do that, you're adding additional load to the last router. So now the router may have to make the packet go through its packet forwarding engine twice. The first time to remove the label and the second time to do the routing lookup. And most routers just respond to this by, it cuts your routing capacity in half because you're doing two lookups. So it's just an optimization. Reasons why you might do explicit null, sometimes you need it for certain features, so it's there as an option. So here's a little bit of vendor terminology warning. Basically, Cisco and Juniper are the two big vendors behind MPLS. There's a handful of other vendors out there that kind of support it, but they don't support the entire suite. They support some portions of it, or they don't have a full implementation. So there's some, for example, Brocade kind of supports it for some stuff, but doesn't have the full range of features. There's some networks like even MRV makes like transport switches, and they support it to a limited degree. But basically, here's the list of terms and the different names that get used. And the different vendors call them by different things, but they're basically the same concept. So MPLS traffic engineering, this is, I think, the biggest reason to use MPLS. So what is traffic engineering? Traffic engineering is when you add a constraint. So you take your classic IGP, that's what's doing non-constrained, non-TE routing. You have a metric or cost value per link, and you run an SPF algorithm, and it finds the shortest path across these links, and it sends your traffic there. Traffic engineering is also called constraint-based routing, because you're saying, find me the shortest path that also meets this criteria. And one of the criteria can be that also has available bandwidth. It can be, there's a bunch of other things that we talk about later. But basically the principle is simple. What you're trying to do is say it's better to take an uncongested path, even if the latency is a little bit higher, than it is to take the shortest link and congest it while you have other circuits that are full.
And can I just do this manually with my IGP cost? And you can, but it only scales up to a certain point. And the more complex your network gets, the harder it is to manage. You get into these situations where you want to move traffic on one link and you change your IGP cost by 1, and it ends up affecting something 20 routers away, and it makes traffic move in a way that you can't easily predict as a human. So this just adds a whole new layer of management capability to your network. But as VJ Gill says, in order to traffic engineer, first you need traffic. So if you don't have traffic, maybe you can actually fit it just fine with standard IGP. So here's kind of an example of where traffic engineering comes into play. Here's a generic network map. And the question is, how do we route from Los Angeles to Chicago? So the shortest path may be this one. You may go up to Salt Lake City and head over to Chicago. But very, very close, within like 1 or 2 milliseconds more, there's the second path. You can go down to Dallas and then come up to Chicago. Then maybe within another millisecond or two of that, you could go up to San Francisco and then come across that way. And maybe within another millisecond or two of that, you could go down to Houston. And depending on your fiber network, these might be reversed a little bit because some of these specific fiber paths, physically go longer than they actually look on the map if you just draw a straight line. But the concept is there's multiple ways to get a packet across your network. And MPLS traffic engineering lets you load balance your traffic in a way that meets the criteria above, which is not to congest the network. So how does traffic engineering actually work? Well, remember that an LSP is a tunnel. It's a unidirectional tunnel between 2 points in the network. And under RSVP, each LSP is assigned a bandwidth value. So you use constrained routing, and you say, find me the path, the shortest path that has enough bandwidth to fit the bandwidth that's being signaled for this particular LSP. And if there's bandwidth available, the LSP gets signaled, and that bandwidth is removed from the available bandwidth pool. So if you had a 10 gig link and you signaled a 3 gig LSP across it, now this link has 7 gigs available. So in the future, if there's insufficient bandwidth, the reservation may go out and it may be denied. It may say, well, we don't have enough bandwidth here, you're going to have to go to another path. And ideally, it'll be routed via some other path, even if the latency is higher. And also, existing LSPs can be preempted for a new higher priority LSP. What this lets you do is set priority for certain types of traffic or for certain customers, and you can map it so that certain customers get access to the lower latency paths or the more premium paths. So it's not QoS in the traditional sense, which is you actually have to be dropping packets. It's a way to optimize who gets access to the lower latency paths without ever having to drop a packet. So here's kind of a diagram showing how RSVP-TE actually reserves bandwidth. So you start by sending out a path message, and you see it goes from router 1 to 2 to 6 to 7 to 4 to 9. Each step along the way, it's being checked against the path to see if it can fit, and if it is, then you get a return back to the previous router of the label that will be used. And it goes out with an RSVP path message. It comes back with an RSVP reservation message, but we're not really getting into the details of the protocol. So the next big question is, well, how do you determine how much bandwidth an LSP needs? That's actually probably the most fundamental question of MPLS that people need to think about when they go to implement it. Because after all, an IP network is entirely dynamic, and from one instant to another, you could have a ton of traffic, you could have no traffic, it could all move. Some BGP session could flap somewhere and it could all go away, it could come back, someone could start sending new traffic. Basically, there's two main ways to do it. The first method is offline calculation, which basically just means the router has no responsibility for it. You go find some way to do it, and then you come back and you program the router. And this is how MPLS was initially deployed. And if you look at the big carrier telco networks that are using MPLS, this is actually how they're still using it today, because they went out and they spent a lot of money to either write their own software or go buy a commercial third-party software to do these calculations.
And they're still using it today. The other method is called auto bandwidth, which is something that the major router vendors implement, where basically what happens is the bandwidth value is calculated on the router itself by looking at how much traffic is actually being forwarded over the LSP. And then periodically that reservation gets updated. So if you kind of look at the two models, the offline calculation model, basically the way these guys are doing it is they're doing this 24-hour period where they do a model. They look at what traffic has come before, what traffic they expect will go over this link, and they kind of model what's the maximum that this link is ever going to take or this LSP is ever going to take, and they set a reservation for an entire 24-hour period. The downside to this is it's very wasteful. So you see there's these huge overlapping, these huge sidebands on each one of these traffic graphs where you're reserving capacity for an LSP that may not need it. And this kind of becomes a problem when you have multiple LSPs that had different traffic patterns. So you might have one LSP going towards a European router that has a different peak time than an LSP going towards an Asian router. So what you really want to see is something more like the bottom, which kind of shows a 1.5 hour adjust interval. And this is making much more efficient use of the bandwidth. So kind of the comparison between the two methods. Offline calculation, you can implement it with any algorithm you want, so you're free to get as fancy as you like. And there's some extremely complex software out there. There's a lot of people that sell software for millions of dollars that will do all kinds of complex LSP planning, and you can manually plan your backup LSPs, and you can add all kinds of weird criteria. I want it to go via this country at this certain way at this certain time. You can do anything fancy you want. But you either have to write the software yourself or you have to buy it. With auto bandwidth, because it runs directly on the router, it's far more responsive to changing traffic conditions. You can have it sampling traffic at a rate that's just not practical for an offline modeling software that has to go out, make a determination of what it thinks traffic's going to be, and then push the results out to the router. So the offline model, typically, they push the results out nightly. In this kind of a model, you could push the results out every few minutes. And it's much easier to implement, and it's also free because it comes with your router. You just turn the knob. The other big thing people use MPLS for besides traffic engineering is data transport services. So the data transport services, the most simple is called an MPLS pseudowire. Just a layer 2 pseudowire, or sometimes it's called a VLL, which is a virtual leased line. Basically, it's just an emulated layer 2 circuit delivered over MPLS. So it's currently standardized by the IETF working group, PWE3, which stands for pseudowire something emulation something. You can use it to interconnect multiple types of media. You can interconnect Ethernet to a frame relay. You're doing this across your MPLS network. It's very useful for migrating legacy transport. So you could take what used to be an ATM point-to-point transport circuit, and you can just slap it on your network. One of the big problems with it is it's actually difficult to load balance. And by load balance, I mean, say you're carrying this traffic across an Ether channel or a port channel bundle. In a packet that's an IP packet, the router can look into the IP header and can hash the packet a certain way so that it can go over different paths without causing packet reordering. But in a layer 2 pseudowire, you have no visibility into what's going across the wire. So because you have no visibility on it, you can't hash on it. So when you take this and run it across your network, you may find that it balances very poorly and all the traffic goes to one link and it leaves another link full or open. And the other interesting thing about this is there's two competing methods for doing the signaling. The one method, the simpler and the most commonly used, is LDP-based signaling, and that's called Draft Martini. Was written by Luca Martini, who used to work at Level 3 and is now at Cisco. And the other method is BGP signaled, which is Draft Compella by Caridi Compella, who's at Juniper. So you can see there's kind of a vendor war going on here. And that's typically called L2 VPN as opposed to something different, which may be called an L2 circuit if it's LDP. And the BGP-based method is more complex because now you have to transport this across your iBGP infrastructure. So you have to enable all the families for it. You have to do it as a route. But it supports auto-discovery, so it makes it a little bit easier to do multi-point, but there's other solutions for multi-point that we talk about in a bit. The big method, and typically you see this in enterprise networks more than anything else, is L3 VPN, which is basically just an IP-based VPN. So what happens is, you as the provider, you end up building a virtual routing domain. You build a VRF on your edge router, and your customer gets placed within that VRF. So your customer will actually speak BGP or IGP to your router, and you will install their routes in your very specific VRF, and then you will use that to transport across your network. The advantage is you can do multi-point. You can have some bank turn up 50 circuits at 50 different cities, and they can all announce their /24. The disadvantage is that it goes into your router, consumes resources. So now you have to speak BGP to these guys, you have to take these routes, it adds to your RIB, it gets installed into your FIB. So it's consuming resources on your router. But another advantage is that it's load balancing friendly, because you know it's directly speaking IP underneath, so you know that it's IP, you can hash on the packet. So it makes it load balance a little bit better. And like I said, typically you see this, and this is like an enterprise type solution. The latest method, not exactly the latest, but one of the big methods that's come out recently is VPLS, which stands for Virtual Private LAN Service. And basically what you're doing is you're creating a multi-point Ethernet switch across MPLS. And this is used to link a large number, potentially large number of customer endpoints into a common broadcast domain. And you don't need to end up deploying a big full mesh of L2 circuits. You can deploy a single instance, and you can connect hundreds or thousands of endpoints into this giant switch. Basically what it's doing is it's emulating the classic functions of a layer 2 switch. So when it receives a unknown packet, it's going to flood it to every device on the LAN, and it's going to do MAC learning to figure out, when it gets a reply back, it's going to figure out this is where it should go from now on. It's going to support broadcasts, so if you have a particular piece of software that relies on a single broadcast domain, you're emulating a giant LAN. And this is also typically more load balancing friendly because you know the contents, you know the layer 2 Ethernet headers underneath. So you're actually, you as the provider router, you're involved in the forwarding of the layer 2 here. And then the third reason that people use MPLS is for fast reroute functionality. So fast reroute is a way to improve convergence during a failure. And what you do is you pre-calculate the backup paths. It's also called local repair, because what you're doing is locally on any one specific router, you've pre-calculated a backup path that doesn't involve communicating with the rest of the network. So you can pre-calculate this path and push it out to hardware. So what happens in a normal IP network is the best path calculation happens on demand. So first you have to have a failure. Then that failure has to be communicated out to every router on the network. And they each go to their next best paths and figure out what that might be. And in the process of figuring that out, typically what's going to happen is one router is going to have to push out those results to another router. So the wider your network is and the higher the latency and the more routers you have, the longer this takes. And you get into situations where it takes several seconds or longer for a big network with a bunch of busy routers to figure out where they need to be forwarding this packet and actually push the results out into hardware. And what happens is a lot of times a transient routing loop will form. So if the packet used to be going this way, and now there's been a failure over here, and so that it decides that it has to go back this way, if these two routers are sending traffic in opposite directions, you create a loop. You don't want that to happen because that takes out your traffic, and especially if you have VoIP traffic or more sensitive traffic than just standard IP, it wipes out the service and people get all pissed off. So with MPLS Fast Reroute, what happens is you pre-calculate the next best path. You also remember to turn your phone off before presenting. And you take the backup paths and you push them into the hardware. So the router already has the results pre-programmed, and it's just waiting for the detection. And the detection can actually happen all the way in the distributed CPUs on the individual line cards. If you're doing BFD, if you're doing sub-second detection, or if you lose link and it triggers an immediate failure, you can push out the results immediately. So you don't have to go through this whole recalculation process. And like I said, everything happens locally on the router, so it doesn't involve talking to the rest of your routers in your network. You have local repair. And because the entire path is set by the LSP, you don't get a transient routing loop. So even if the path is briefly suboptimal, it's better than dropping the packets completely. There's a bunch of different protection schemes out there. The simplest is called one-to-one protection, or a detour LSP. This is kind of the way that it was done first. And basically what happens here is every individual LSP has a primary path and a backup path. So using RSVP, you signal it in both directions. The downside here is that you're consuming a lot of CPU, a lot of resources, a lot of signaling overhead. You're out there reserving these, double the number of LSPs that you have to have. And it's not just double, it's double at every point. So if you have 5 routers along your network, each point has to have a bypass for each LSP that goes through it. So you end up, exponentially multiplying the number of LSPs that you have in your network. But one advantage is the label depth stays at 1. You're not stacking things. Then you get into more complex protection with many-to-one protection, or what's called facility backup. And what you do there is you make a single bypass LSP that's capable of protecting multiple regular LSPs. So during a failure, you take the LSPs and you slap them in the bypass and you send them off, and it gets you around whatever the particular failure is, keeps the packets moving. And inside of that, there's link protection and node protection. So link protection is also called next hop backup. What you're doing is you're looking at every link on the network and you're saying, if this link goes down, what's the way to forward the packet that goes via a different link? And then you have another type of protection called node protection, or next hop backup. And that's saying, what happens if the next router that I'm talking to fails? What's another router, completely diverse router, that I could talk to that doesn't go through this path? And so in this diagram, you have 5 routers with your regular forwarding path with no protection. Here's what happens if you add link protection. You go out and you look for a bypass path that doesn't go over the link that's being used. Here's what's happened if you use node protection. You go out and look for a way to a different router other than the one that you're directly talking to. And then here's what happens if you use both. And so for a relatively few number of LSPs, and this scales by number of routers, not by number of LSPs, you now have protection for every LSP that forwards over all 5 of these routers. So if any one of these links or any one of these devices dies, you can immediately put the packet into the next LSP, kick it off down the road, and it'll still get where it's going. So some more details about MPLS auto bandwidth. Technically, each algorithm is completely router vendor independent, but it just so happens that Cisco and Juniper both implemented it the same way. You can pretty much guess what happened there. Someone wrote it for Cisco, and then they went to work for Juniper, and then they wrote the exact same thing. Basically, the steps all look exactly the same. So what you have is you start with a statistics interval. It's the interval over which the bandwidth is measured. So for example, you might configure a 60-second statistics interval if you want, like a 1-minute average, and it's kind of a good way to detect microbursts. You might do a 5-minute average if you want it to be a little slower. But every time, every 60 seconds or whatever you configure it, you determine this is how much bandwidth is being forwarded across this LSP. Then you have an adjust interval, and you say, every adjust interval, I take the biggest sample that I saw from those statistics intervals, and I go out and signal that as the new bandwidth. So for example, I might take a 60-second stats interval, and then I might have a 300-second adjust interval. So I say, over the last 5 minutes, what's the biggest 60-second sample that I saw? That's what I'm going to go out and signal with. And there's usually some there's some mechanisms in there where you can say if it's less than X% difference, then don't bother, something like that. So you there's some ways to reduce signaling. So here's kind of an example of where auto bandwidth works really well. So the black lines are they're showing adjust intervals. So there's 3 adjust intervals here, and the blue dots are showing statistics. So each one of these is a measured point where you're saying this is how much traffic is passing over this LSP. So in the first one, you have a stats interval. You pick your highest bandwidth sample, which is like 32 or something, and then for the next adjust interval, the red line is showing what the reservation is. So that reservation is going to stay in place the entire time, but while that reservation is in place, you're going to go out and resample the bandwidth, and you're going to say, this point here at 27 is the bandwidth, and so the next stats interval, you're going to go out and signal that, and it's mostly going to work well. Here's what it looks like when it doesn't work well. If you have big traffic spikes that happen per LSP inside of these adjust interval windows, you see here that there was a big traffic spike, pretty brief, but it happened enough to get the reservation up really high. So then the next interval, the reservation is much higher than the actual bandwidth. Auto bandwidth adjusted this, and it says, hey, I'm not actually using that much bandwidth, I'm going to bring this down, and then reserve is a much lower value, and then you see traffic ramp up again. So you really want to make sure that your adjust intervals are constrained to a size that you're not going to see huge fluctuations in traffic. Most vendors also implement one of the two or both, overflow or underflow. And basically this is an optimization, so you don't have to go out and set your adjust interval to something really, really low, because every time that happens you're potentially resignaling. So you say, have a higher adjust interval, but I'm also, during this adjust interval, keeping tabs on the bandwidth. And if a certain number of statistic samples go above a certain rate, so I might say if I see two statistic jumps of 60 seconds that are above a certain threshold, I don't wait, rather than wait 30 minutes or an hour to do an adjust, I might say do it now because something has changed. You artificially trigger the adjust interval to go out and adjust things. And this is very useful for catching big bandwidth changes without having to burn your CPU constantly adjusting things. But one downside is you need underflow. You need the same thing in reverse. You need to be able to say if traffic goes down by a certain amount, I need to recover bandwidth. Or what ends up happening is BGP changes, and so traffic shifts from one LSP to another LSP. And so overflow will catch the one LSP going up, but it won't catch the other LSP going down. And so now you're trying to reserve more bandwidth than you're actually using, and you might get into a situation where either you're sending this thing over some really high latency path that you don't need to be sending it over, or worse yet, you're not able to get enough bandwidth at all, and you aren't able to forward the packets. So you kind of need both sides of the equation. There's some more details about how MPLS works. Like I said before, RSVP-TE LSPs have priorities, and the LSPs have the ability to preempt each other to acquire the bandwidth that they need. There's two values that they use to do this. One's the setup priority and the other's the hold priority. The setup priority just means how much do I want to try to set up this LSP if it doesn't exist at all. And the hold priority is how much do I want to try to hold the reservation that I have. So there's 8 priority values for each LSP, 0 through 7, 0 being the highest priority. When you do the preemption, there's 2 ways that you can do it. One is a hard preemption where you just go out and you say, tear down this LSP, it's gone. And this will usually have some kind of an impact to the packets being forwarded because the LSP goes away. The other method that you want to try to use for most situations is called a soft preemption. And in that case, you give the LSP some length of time, a few seconds or something like that, to go out and find bandwidth on a new path and then tear itself down. And this prevents the preemption from being disruptive. So here's kind of an example of how preemption works. Here's an LSP going from vet to kitty through amber lamps. It's a 7 gig LSP. It's fitting across a 10 gig link, and that's fine. And now you want to reserve some more bandwidth. You have what is that? A 4 gig LSP coming from Supra, going through amber lamps and going over to kitty. And what's going to happen here is you're not going to be able to fit, this is 11 gigs of bandwidth that you're trying to fit down a 10 gig pipe. So what's going to happen is the first LSP is going to get preempted because the LSP from the vet to the kitty is of a lower priority than from super to kitty. And so this LSP is going to end up getting rerouted through Bailey Boo. Don't ask. There's an inside joke in there somewhere. You also do LSP optimizations because what happens is over time the network topology can change. You can have IGP cost changes, you can have new links get added, you can have links come down. You want a periodic optimization process that goes through and has the ability to change which paths your LSP is going over. Normally this is kind of a background process, so you might configure it to go off like every hour or every 30 minutes, whatever you choose. And it looks to see, is there anything that I can do to move this LSP to a better path within a certain definition of better. And so if it's going to move it just a little bit better but not enough, it may not move it at all. But if it finds a much better path, much lower latency, where there's much more available bandwidth, et cetera, it's going to try to move the LSP to a better path. And there's a lot of routers out there that can do smart optimization, where what happens is when a link goes down and then comes back up within a certain period of time, you go ahead and immediately kick off the optimization. But if you see that same link flap, 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 flap again, you don't try to re-optimize every time. And that saves CPU across your network, prevents a flapping link from going nuts. So when you do the resignaling, there's a feature called make before break or adaptive LSPs. So what happens when you resignal an LSP for any reason, and it doesn't matter if you're doing it because of a reoptimization or you're doing it because you're changing the bandwidth value, whatever. There's no way to update an LSP. What you do is you completely tear down the old one and you build a new one. So when you do that, you want to do it in a way that's non-disruptive. So you try to do a make before break, which basically just means the new LSP gets signaled and then you tear down the old one. If the LSP is going over the exact same path, what happens is the router along the path that sees both LSPs knows one of these is new, one of these is going away, and I'm not going to double count. But if it resignals on a path that goes to different routers and the routers don't know about this, doing this kind of a adaptive make before break LSP will double count the bandwidth. So you might get into a situation where because you're double counting the bandwidth for a few seconds, now all of a sudden your network looks like it doesn't have enough capacity and some LSP will fail or reroute suboptimally. So it's a trade-off that you have to make. So now that you have these LSPs, the question is how do you go about using them for your IP traffic? So there's basically two ways to do this. You can use a static route. It's not very practical, but you can actually do some pretty handy quick and dirty traffic engineering. Like if you've ever, I've got this packet in New York and I really want to get this, this prefix, I really want to get it to LA, but I don't want to make the entire rest of my network bring this prefix to LA. You can drop a static route and you can say, use this LSP. So it's actually a really handy way to do some quick and dirty traffic engineering, but it's not practical for everyday use. What happens when you want to actually use the LSPs to forward your IP traffic? On Juniper, it's called traffic engineering shortcuts, and on Cisco, it's called auto route. And what this does is it changes the way the next hop resolution is done. On Cisco, it's done transparently. It's just a silent modification of their SPF algorithm. On Juniper, you're adding it to your inet.3 table. The results are the same. What ends up happening is you use the LSP that gets you closest to the path closest to where you're trying to go along the tree. Even if the destination endpoint doesn't speak MPLS, it's going to find the closest one. So, for example, in this diagram, say you're trying to get to P4 or P5 and they don't speak MPLS, it's going to find the LSP that goes to P3 because that's the closest router along the path to the destination. And in this other example, same thing. You're trying to get to P8. It's going to find the path that goes closest to it, which is an LSP to P7, so it's going to use that. Some considerations about MPLS. MPLS actually lets you hide traceroute hops. It actually doesn't let you, it forces you, and then you have the option to kind of disable that. But if you think about what's actually happening, when you're MPLS forwarding a packet, you're not actually routing it. You're label switching it. So technically it doesn't go through the IP forwarding process, so there's technically no reason that the TTL value ever needs to be decremented. And if you choose to leave it that way, then what happens is the LSP shows up as a single hop and traceroute, and you kind of hide the innards. Some people prefer this. I've heard a bunch of reasons, everything from, well, my customers think that somehow packets forward better if they don't see the routers in the middle. They think that it's like better express route, which is actually sadly true. There's a lot of people that really think this is a performance metric. So if you just kind of hide it from them, then all of a sudden they think your network is just super cool and awesome. I've heard everything from that to there's a lot of applications out there that have some really hard-coded low TTLs where people were running into situations where applications would actually break when they built their network above a certain size because someone hard-coded a TTL of 30 somewhere 10 years ago and thought that would be fine, and it turns out it isn't. But one of the some networks will actually choose to use MPLS-only cores. Talked about that previously, where you don't even carry an IP route at all. But one of the downsides to this is if you choose to decrement the TTL so that traceroute works correctly, well, what happens is the way traceroute works, you decrement the TTL to 0, and then the packet gets dropped, and you generate an ICMP message. You send it back to the original sender, and you say, hey, I dropped the packet here. Well, what happens if you drop the packet inside an MPLS core that doesn't carry IP? Where do you send it? So a workaround for this problem is a feature called ICMP tunneling. And what this does is say, anytime the router has to generate an ICMP message for any reason while the packet is in transit over an LSP, I'm going to go ahead and forward the ICMP message all the way to the end of the LSP before I start doing my routing lookups. And this works, you get the packet, but what ends up happening is every hop inside the LSP looks like it has the exact same latency of the last hop. And so all of a sudden you get really confused end users popping tickets with your NOC and complaining, and it's not actually broken, but it sure looks screwy. So that's a downside to doing that kind of thing. And that's another reason people will choose to hide their hops. MPLS has some features called link coloring. Also called affinities or admin groups. Basically, it's just another constraint in the CSPF algorithm. So what's happening is you're allowed to signal 32 unique color markings, and the colors are entirely arbitrary. It's your network, it's your policy. You set whatever you want to set. But you make a color and you say this color means something to me, and then you add a link, you add that color to a particular link, and that gets flooded out across the network. And so the RSVP knows that these particular links are of this color, and then you write a policy that says, I want to use this color link for this type of packet or whatever. So it's not just great, it's great for specifying geographic political boundaries. So there might be situations where you need to keep the packet from crossing into a specific region for whatever legal reasons or whatever. There's situations where you want to be able to completely move things off a link to do maintenance. There's situations where you don't want a certain type of packet traversing a certain link. So, for example, you might have core LSPs within your network that you don't ever want going through a metro network and then coming back out, because you probably aren't going to have the bandwidth for that, so you don't even ever want to consider it. So you can block that kind of a thing by having a link color. There's shared risk link groups. And what's happening here is when MPLS does its backup paths, it may not fully be able to appreciate what's the underlying infrastructure going on. So, for example, it might pick a backup path that shares the exact same physical conduit, transport gear, cross-connect, whatever, with the primary path. And if something is going to happen and it's likely that two links are going to fail at the same time, what happens is you can put them into the same shared risk link group, and then that says when you go to build your backup paths, you always look for something that takes a different shared risk. So, for example, there might be multiple ways to get from Chicago to, you might have a direct path from Chicago to New York. You might have an alternate path that goes Chicago, Cleveland, New York, but it turns out that those pieces overlap a significant amount of the infrastructure. And so you want to build a bypass LSP that doesn't touch that same shared resource. you put those two paths into the same SRLG, and so now you can build a bypass LSP that avoids that. So you're guaranteed that even if you do have to bypass something, the latency is going to be higher, but you're saying it's so much more likely that I'm going to lose both these links at once that I'm willing to have a higher latency to guarantee that I'm going to get my fast reroute. And that, if you have customers that are very sensitive to having any kind of a drop, that's the kind of thing that you want to implement. So there's a couple downsides to MPLS. No protocol is perfect. MPLS definitely least of all. One of the major drawbacks to it is that it actually hides the topology from BGP when there's multiple exits. So say, for example, that I peer with a network in San Jose and Los Angeles, and I've got traffic coming from Chicago that would normally go directly to San Jose. And that's because Chicago to San Jose is closer metric-wise than Chicago to Los Angeles. So say there's an issue, there's a circuit cut, there's a capacity issue. The LSP is now forced to reroute via the south via Los Angeles. In an IP network, what would happen is when the packet, even though the packet in Chicago might think that it's still being forwarded to San Jose, when the packet actually gets to LA, the LA router might say, hey, I can forward this locally, and it might do it. With MPLS, you're hiding that because MPLS predetermines the forwarding path from the initial point. So that can actually be a good thing or a bad thing depending on your goals, but it kind of looks like this. In this situation, say the blue LSP, the blue path is not able to forward the packet, it has to go the purple path. You might want to be able to just forward the packet out Los Angeles instead of hauling it all the way back out to San Francisco, adding extra latency. And there's plenty of examples that are just more complicated and harder to show where you can introduce a whole lot of extra latency or bad things to your network by doing something like this. But you might actually consider this a good thing because if you're doing traffic engineering and you're trying to balance this traffic between these two exits, you might not want a link failure to shift the traffic that goes out your edge network. So it's a curse or a blessing depending on how you look at it. Another big problem is that the actual LSPs don't create themselves. So unlike other routing protocols where you just kind of turn on the routing protocol and all the routers go out and talk to each other and come up with some magic, MPLS doesn't do that. The routing protocols are just used to exchange labels. They're not actually used to build LSPs. So basically what happens is the vendors have said building the full mesh of LSPs is an exercise left to the operator. Enjoy. So basically, there's two solutions. Either you're going to go out and build a script to do this. You're going to go quickly insane if you try to do it manually and you have any number of routers. Or you're going to have to purchase a commercial software solution. There's software, Wandle, Keratin, there's a bunch of others that are software specifically designed to look at your network and build LSPs. Some vendors offer what's called auto mesh capabilities. So, for example, Cisco can do this, where what you do is you define an access list with a bunch of IPs, and then you define a template, and you say, go create a bunch of LSPs to these ISPs using this template. The downside is there's no way to manually control any individual LSP after that point. And also, it turns out Cisco, the access list type that you have to use to create this, there's no way to actually remove an individual IP. So if you want to remove something, you have to tear down the entire access list, which tears down every LSP being generated by the router, which is probably bad for your traffic. So there's a lot of, clearly there hasn't been much thought given into how to make this actually work and scale correctly. Because most people out there are using some form of script to push their LSPs out there. Another big problem, big LSPs don't fit down small pipes. So what happens here is an LSP can only be moved as an atomic unit. It can go here or it can go here, but it can't do both. So if you have a relatively large LSP relative to the size of the circuits that they're going over, you're not going to be able to efficiently pack them. So for example, say you have 3 individual 6 gig LSPs and you have 2 10 gig circuits that you're trying to fit them over. What's going to happen is 2 of the LSPs are going to fit, the third one's not going to fit, and either it's going to find something that's, more suboptimal to route across, or it's not going to be accepted at all. And at the same time, you're going to be left with these 2 circuits that are only using 60% of their bandwidth. There's one workaround for doing something like this is if the 2 paths are going to the same place, you can bundle them into a link aggregate. So you can now have a 20 gig circuit, and so all three of those LSPs would fit over that link. The downside there is if those two circuits that you're making part of the bundle have different performance characteristics, say one's 10 milliseconds higher latency than the other because it's a diverse fiber path, you're not going to have any visibility into that. So generally, it's better if you have individual circuits that take different paths that you signal individually, because then RSVP can say, try to fill up the lower latency path before I fill up the higher latency path. But sometimes you get into situations because of this where you can't do that. Another workaround is to create multiple parallel LSPs. So say, for example, instead of having 3 60 gig LSPs, you split them into thirds and you say, I now have 9 2 gig LSPs. Well, now that's much easier to pack efficiently. Ideally, what you would want to do is you'd want to have your auto bandwidth process be able to look at an LSP and say, if it goes above a certain amount, to be able to fork it. This is especially important if you run mixed link sizes across your network. Let's say, for example, you have a bunch of OC48 links. You may have a 3 gig LSP that's part of your big high-performance multi-10 gig network over here, and you have this smaller network over here, and for some reason you need to route the LSP through there. You can't fit a 3 gig LSP across an OC48. There's only 2.5 gigs of capacity. So that's a problem. There's a bunch of gotchas with auto bandwidth too. We already talked about some previous examples of where the LSPs get incorrectly sized, and that's just because of changing traffic patterns. But there's also situations where auto bandwidth itself, because the problem is what you're doing is you're measuring the size of the LSP based on how much traffic is actually being forwarded. So if there's anything that creates an impairment to that traffic being forwarded, auto bandwidth is going to back down. So for example, there's a bunch of people out there that oversubscribe their links. They may say, I want to be able to push 110% over this RSVP link. I don't know why you do that, but there's people that do. What happens is, because auto bandwidth doesn't know anything about congestion, if RSVP tries to map these two or these multiple LSPs across this link and it creates congestion is going to cause TCP to throttle back. The IP rate of the traffic is going to go down, and now auto bandwidth is going to adapt to this new rate. So you might get into a situation where auto bandwidth continues to overpack LSPs onto a link, and the only way to prevent it, or the only way to fix it, is to go in manually, figure out what's happening, and go in manually and boot some of the LSPs off. It can be a pain. Another big problem is if your router doesn't have accurate visibility into the actual utilization across the link. And this can be a big problem if your router doesn't see layer 2 overhead. For example, almost all Juniper routers fall into this category. They see the IP, but they don't see, at the part where the router is actually making decisions and gathering statistics, they don't see the layer 2 overhead. So if you have a denial of service attack, say for example a 28-byte UDP flood, it actually consumes 84 bytes on the wire across Ethernet. And so you get into a situation where your link is now exhausted at 41% of capacity instead of what you might expect. And auto bandwidth has no visibility into this, and so it's going to continue to pack more traffic than you can actually pass onto the link. So you can kind of work around this type of thing by just being conservative, not oversubscribing your links, or leaving some amount of headroom so that if your link does get close to full, that you kind of pull it off. But that's a downside to using Ethernet links, even though they're cheaper. And that's basically it. Questions? Microphone.
Is there any functionality for evaluating whether the stealing of the latency is going to be hit? In other words, if you have a least priority reservation and you're going over that traffic and you don't want to see 150 milliseconds plus, is there any metric or mechanism by which you can keep that at your
I don't think there is, and that's. Can you say that on the microphone, because that was kind of complicated, so people can hear. Sorry, but it's a big room.
So my question was, is there a mechanism or method by which you can tell that your RSVP network is broken since your least priority traffic is not getting the latency that it needs, for instance, VoIP traffic,
is now being pushed down to the bottom of the traffic and getting, say, 200 milliseconds plus latency, and that's not sufficient for your needs.
So you could do something like that with your external monitoring system. So you might start saying, hey, I'm seeing packet loss, or hey, my application is seeing high latency, and use that as a trigger to say something's not right. I need to go in and manually kick things. But there's no mechanism in the router for it to look at that and see what's going on. It's one of the things where, because so many of the big classic telco providers are still using offline calculation, there's actually not as much auto bandwidth out there as you might think. And so there's actually still some bugs floating around. I've got cases with router vendors open right now where they're miscalculating bandwidth. And that's just a function of more people need to use it. Generally speaking, when it works really well. And so it's worth considering, because it can really improve both the manageability of your network and the efficiency of which you use the resources. But there are still some issues out there where you kind of got to keep an eye on it, make sure that it's doing the right thing. Anybody else? Did I put you guys to sleep? Okay then.